Alright guys, so today we're going to learn how to find the derivative of something known as an implicit function. So that's the goal for today. So by the end of today you should be able to tell me what a function is, if it's implicit or explicit. And then after that you should know how to find the derivative of an implicit function with respect to a specific variable. So the beginning of our lesson is going to be focusing on this little statement down here. It's something that we just kind of been saying a lot lately but haven't been spending a lot of time on. So it's going to get a little bit more focused today. What does that mean to do something with respect to a certain variable? Well, let's take a look at it. Alright, so let's talk about functions for a second here. So if y depends on x, that means that the value of y is based on whatever you have for x. So for instance, suppose I gave you this equation right here. Well, usually what we would do is we would pick a number to plug in for x, and that would tell us what our y is. So we got to randomly pick the x, which means we are free or independent to do whatever we want with the x. You could pick whatever you want to for the x. But the y outcome depends on that. So whatever you pick for x, that's going to affect what you get for y. So we say in that case that y depends on x. Another way of saying that is to say that y is a function of x. Okay, once again, all that means is that y depends on x, which means that y is a function of x. So if I tell you that y is a function of x, that means that if you plug a number in for x, you'll get a specific answer for y. So if y is a function of x, this is how we write it. So this is the math language for this concept of y depending on x. So if y depends on x, you know what that means? That means that as x changes, y will change. Okay? And whenever you talk about that, if you talk about the change in x and you compare that to how fast y is changing, you get a derivative, a slope. How fast does y change as x is changing? So like when you're talking about a slope, you go over 1 up 2, for instance, right? Well, what that means is that if your x increases by 1 unit, your y is increased by 2. That's what that means. So that tells you how fast is y changing as x is changing. And so if y is a function of x, then that means that there's a derivative of y. There's a slope of y with respect to x. In other words, x is the one that's determining how fast y is changing. Okay? So that's what that means. And that's why it's kind of important whenever you're doing a function. Like for those of you guys that have calculators, there's two types of calculators out there, if you guys have been working on them. One looks like this and the other one looks like this. Okay, but either way, you always have to type in your function first, and then you have to type the variable x in there. So that's what it looks like for the TI-83s. For the TI-84, you have to put it here. But it's important because then, after you put your function in there, your function knows, okay, this person wants me to find out how fast this is changing as this variable is changing. Okay? The reason that's important is because actually there's some functions that depend on more than one variable. So if you don't specify which variable is the independent variable, then that's going to affect your outcome for how fast the output will be changing. So we do have to specify what the input variable is. Okay? So the rate of change of y with respect to x means how fast y is changing as x is changing is f prime of x. Okay, I think this is this is a confusing way of writing. I should have maybe put a comma here, or maybe replace the equals with an is. So the rate of change of y with respect to x is denoted f prime of x. Okay, so there you go. So y depends on x means that y is a function of x, and f prime means how fast is the y changing as x is changing. Okay, so that's some stuff about functions there. Now let's add another thing. So let's say that y is a function, but it doesn't depend on x. So for example, it doesn't really matter, for instance, I'm trying to think of an example here. So let's go with an old proverb. I don't care if you agree with it or not. That's not important. But let's go with the old proverb. There's an old proverb that says, money can't buy you happiness, right? Well, what that means is that money does not depend, actually, let me back up, not money. Happiness does not depend on money, which means happiness cannot be a function of x. Okay, so if your happiness doesn't depend on the amount of money you have, then as the amount of money you have is changing, it shouldn't affect your happiness because they're not related to each other, right? So if y does not depend on x, then that means that y is not a function of x, and therefore y will not change when x changes. So therefore, the rate of change of y with respect to x is 0. That means as x is changing, y will not change at all. Its rate of change will be 0 because they're not dependent on each other. So there you have it. So keep those facts in mind. We're going to build on those and use those in a minute. But just some information about what it means for something to be a function. Okay? So let's talk about a new topic here. So today we're learning how to find the derivatives of implicit functions. So obviously you need to know what an implicit function is. Well, an implicit function is really just a way to write a function so that the output variable is not by itself. So for instance, here, this is an explicit function. Why? Because the y is all by itself. Y is f of x, so you could write it like this, right? The y is all by itself. You know what y equals. You could plug in a number for x and you'll get the answer for y as a result, okay? This is an implicit function. There's no y equals here, okay? So we don't have the y by itself. That's called an implicit function. These two functions are actually the same function, kind of. There is a slight difference. I'm not going to get into it right now. I'll tell you what the difference is. If I put a plus and minus, now they're the same function. But putting that aside, let me show you guys why these are actually the same exact function. If I were to square both sides, on the right side, the square cancels out the root. And then I can subtract the x on both sides. And as you guys can see, I end up with the same exact thing. So I just moved things around doing math, but I didn't actually change what the equation is. So technically, I should be able to just plug in a number and get a y value. I should be able to do the same thing down here. But what makes this, the top one, an explicit function is the fact that the y is already by itself. It's already solved for. Whereas down here, the y is not by itself. It's not solved for. Okay? So today we're going to learn how to find derivatives of implicit functions. How do you find the derivative of a function when their input variable, the output variable is somehow buried inside the equation itself? It's not by itself. That's our goal for today. All right. So let's do a little bit of review before we get into the new stuff. So given that y equals f of x, find f prime of x. So if y equals f of x, right, if I want to find f prime of x, that means just find the derivative, right? Okay, so to find the derivative, then we want to, first of all, rewrite the original equation a little bit. So we don't like those square roots, right? So I'm going to write it like this. And that way, if I want to find the derivative, I'm going to do the chain rule, because we have an outside function, which is the half power, and an inside function, which is x plus 1. So the derivative of the outside function is 1/2 times the quantity of, take 1 away from the power, -1. negative 1/2, times the derivative of the inside, which is 1. So, in this case, since we have a negative power, that's going to move the x plus 1 into the denominator. Right? And a 1/2 power is just a square root. So here is the derivative of that function. And that's just stuff that we already know. That's stuff we're familiar with. But we're going over it because I want you guys to be prepared for the new topic today, which is how do you find the derivative of an implicit function? Now, the problem I'm about ready to do is the end game of our lesson. This is what I want you guys to be able to do by the end of the day. So what I'm about ready to do is a lot of work, and it might be a little weird looking, but I just want you guys to kind of see what we're trying to get to. All right? Now, before we get started, though, this function is the same function as the last slide. It's just written in implicit form. Now, if I wanted to find the derivative of this function, which is what it's asking me to do, you might think, well, okay, I know what we could do, Mr. Bailey. We could just get the y by itself and then do what we did on the last page and we're good to go. Yes, you could do that. But I'm going to show you guys another way to do it where you don't have to get the y by itself. You can actually just find the derivative while it's in implicit form. Now, you might ask, well, why would you want to do that? What's the point of learning something new when you can just use old stuff, right? Well, the reason why is because there are actually many functions where you can't get the y by itself. It just doesn't work. There's not algebra moves that can make it possible. So we need a way to be able to find a derivative even when it's in implicit form. And so that's our objective today, is how do we find the derivative of this without having it in explicit form? So here's the steps. The first thing we're going to do is we're going to put some brackets around it. And I'm going to put the symbol on the outside. And what this symbol means is I want to take the derivative of everything on the inside. So let's go ahead and do that. But before we do, I want you guys to notice something special. We have two variables in this problem, but one of them is not just a variable. The y is not just a variable. The y is actually an entire function, right? The y is a function of x. So y is not just another variable, it's actually a function in and of itself. So instead of y squared, I'm going to replace that with f of x squared. Okay? So that's weird thing number one I want you guys to pay attention to. All right? Next thing. Here we go. So let's go ahead and take the derivative of every part of this expression. So I'm going to take the derivative of 1. And you guys know the derivative of a constant is 0, right? I'm going to take the derivative of negative x. Now, when you have a constant multiple problem, all you do is you take the multiple off when you find the derivative. So the slope of that, or the derivative of that expression is negative 1. And then this one's interesting because that's actually going to be a chain rule because it's a function, f of x, inside of another function, squared. So we do a chain rule. The derivative of the outside, move the 2 to the front, take 1 off the power. And we multiply that by the derivative of the inside. So the derivative of f of x. So I'm just going to write it like this. Now, this is a 1. It's not a prime, which because it's a power of 1. This one over here is a prime. Now, instead of doing primes, let's go ahead and go back, or I'm sorry, instead of doing f of x, let's go back to our y's. So I'm going to replace f of x with y, and I'm going to replace f prime with y prime. It just looks nicer. Easier to look at, easier on the eyes. Now, the problem is asking me to find f prime of x. In other words, it wants me to find y prime. So I want to get y prime by itself. So if I wanted to get y prime by itself, what would I do? The first thing we would do is we would add 1 on both sides, right? And that would leave me with y prime times 2y is equal to 1. Now what would I do to get y prime by itself? I would divide both sides by 2y. And there's my answer. That's the lesson that you guys need to know how to do today. Some of you guys might think, cool, I can do that, and you might be ready to start, but we're still going to take some baby steps to get there. But if you're confused, don't worry about it. We're going to try to slowly get you there and walk you there step by step. But that's the big idea. That's what I want you guys to be able to do by the end of the day. But before I go any further, remember on the last slide, what did we get? We got this, right? But we know that this function is really the same thing as, I can change my slides here, it's really the same thing as this function, it's written differently. So why do their derivatives look so different? Well, actually, their derivatives are exactly the same. Go back to the last slide once again. What does it say y is equal to? Y is equal to this, right? So if I come back to this other slide over here, and I replace the y with what y equals, as you can see, we actually have the same exact derivative. We just got there in a very different way. So we got there by doing implicit differentiation is what this is called. Finding the derivative of an implicit function is called implicit differentiation. Okay, so that's our goal for the day. I want you guys to be able to do a problem like that. But before we do, I want to talk a little bit more about this concept of differentiating with respect to x. It's a phrase we say a lot, but we kind of we haven't really been given a lot of attention, but it actually matters. It actually matters. Okay, so number one is not a trick question. I'm asking you to find the derivative of this expression with respect to x, and you would do it the way that we've been doing it since our first day in this class. So what is the derivative of x cubed? Hopefully you know that it's 3x squared. You move the 3 to the front, you take 1 off the power. But number 2 is different. Okay? Here's the difference. In this case, I'm not just taking the derivative of x cubed, I'm taking the derivative of y cubed. And that's significant because, as we know from the top up here, y is not just another variable. Y is actually a function of x. And therefore, we would have to do the chain rule on this problem. Okay? So, let's do that. The inside function is f of x. The outside function is that quantity cubed. So, derivative of the outside times the derivative of the inside. So the derivative of the outside would be 3 quantity squared, and that quantity is f of x, times the derivative of the inside, which is f prime of x. And if we go ahead and just replace the f of x's with y's, this is what it would look like. Now, that's the long way, but that's the way that actually helps us understand why the answer is what it is. It's because we have a chain rule. But from now on, we're going to skip all this. We're not going to do that anymore. You can actually just jump straight to this answer. And here's why. Compare the derivative of x cubed and the derivative of y cubed. Look at their answers. This one is 3x squared. This one is 3y squared. The only difference is that this one has a y prime next to it. That's the only difference. So in other words, whenever this variable doesn't match this variable here, basically just take the derivative like you normally would, and don't forget to put a y prime next to it. So let me give you another example. Suppose I had this. Let's say I had sine of y. And I wanted you to find the derivative of this with respect to x. Well, here's what you would do. Just find the derivative like you normally would. What's the derivative of sine? The derivative of sine is cosine, right? But we're just going to multiply it by a y prime because there was a chain rule involved. And that's because these don't match. Right? Now, it's a little bit more complicated, though, than these just not matching. And you're going to see why in the next problem. Not only that you're going to do that if they don't match, and if that y is a function of x. Let's take a look at number 3, though. Number 3 is going to be a little bit different. So let's just say we're going to ignore this statement that I have written here for now. You can actually do exactly what I just said to this problem. Take the derivative of it like you normally would, because these don't match, right? Just take the derivative of it like you normally would, times, and multiply it by a prime. M prime. That works. But I want to show you guys something interesting here. in this problem, I'm telling you that m is not a function of x. Now, in the beginning of class today, I shared some information with you guys about what happens if something is not a function of the x. So, if y is not a function of x, or I guess in this case we could say m, if m is not a function of x, then that means that m does not change when x changes. And that means that the rate of change of m with respect to x is 0. In other words, m prime, the rate of change of m with respect to x, is 0. So, keeping that in mind, let's go back to where we were there. Since these didn't match, we just did the derivative like normal, but we just put an m prime next to it. But we also just saw in the last slide that m prime is 0 for this problem because m is not a function of x. And therefore, 0 times anything is 0. So from now on, instead of going through all that crazy thought process, here's what I want you guys to know. You kind of have a pronged thought process. So first thing is you're going to say, does the variable match the dx? Okay? So does the variable match the dx? If the answer is yes, like on this one, if the variable matches the dx, then just do a normal derivative. If the answer is no, we have to ask ourselves, is it a function of x? Actually, let me put it here. Is it a function of x? In other words, does that variable depend on x? If the answer is yes, like here, when you take the derivative of that, they don't match, but the y is a function of x, as it says up here. If the answer is yes, then just do a normal derivative and multiply it by a y prime, or whatever, right? M prime, g prime, whatever letter you're working with. If the answer is no, it's not a function, it's wonderful, it's even easier. The answer is just 0. Okay? So there's your process, and that's what this one was. Since m is not a function of x, the derivative of this expression with respect to x is just 0. So there's your three-pronged decision process. Does the variable match the dx? If yes, just do a normal derivative. If not, you have to ask yourself, is it a function of x or not? If it is, do the normal derivative and just put a prime next to it. If it's not, it's 0. So let's apply that thought process here to this problem. I want to find the derivative of this expression with respect to x. So, does the x match the h? The answer is no. So now I'm here. Next, is h a function of x? Is it a function of x? The answer is no, it's not. They tell us it's not. Therefore, the answer for that one's going to be 0. That part of our expression will not change with respect to x. There is no rate of change of h with respect to x. It's just 0. Next one. Does the variable match the dx? And the answer is yes. When that happens, just do a normal derivative. So what's the derivative of 3x? It's just 3. Constant multiple rule. Next one. Does the variable y match the dx? The answer is no. Those are different variables. Next question. But is y a function of x? And the answer is, they told us in the very beginning, yes it is. If that's the case, we do a normal derivative. So what's the derivative of y? Well, that would just be 1, right? Because its constant multiple is 1. But we also multiply it by a y prime. Okay? So there is this concept of what does it mean to differentiate something with respect to x? Well, it could mean 3 different things. So there's your decision process you're going to go through as you do these problems. All right, now, here's some for you guys. I want you guys to do numbers 1 through 4. And pause the video here, and when you're done, you will see the solutions, and I'll explain it to you. Okay, so here are our solutions. As for number 1, we're finding the derivative with respect to x, of course, and all these terms have x's in them. So you're just going to do the derivative like normal. So no surprises there. Number 2, we're finding the derivative with respect to x, but each of the terms that have variables are y's. So you would take the derivative like normal. So y squared would be 2y, 3y would be 3, and negative I would be 0. So, but since these don't match, and y is a function of x, that means we need to multiply them by a y prime because there was a chain rule that happened to make that work. Okay? And we don't need the 0, obviously, so that's why we have the boxed answer there. All right, part 3. Here, they don't match, so you take the derivative like normal. Derivative cosine is cosine. And then you multiply it by y prime, because y is a function of x. Over here, m is not a function of x. Therefore, when you take the derivative, that's just 0, it goes away. All right, the last one, I switched the letters up on you a little bit, okay? But the same principle applies. This letter matches this letter, so you just take the derivative like normal. The derivative of 3g with respect to g would be 3. Here, they don't match. So is a function of g? Yes, it is. So therefore, we take the derivative like normal, which would just be 4, but then we're going to multiply it by an a prime. By the way, another way to write a prime in this case would be the derivative of a with respect to g. That's the same thing as this. It's just another way to write it. Another way you could write it is you could say f prime of g. That would also work. Okay? So either of these symbols could have gone right here. I just find it a little bit easier to use a prime. Okay? So, now that we've done that, you guys are now ready to do the main goal of today, which is to do implicit differentiation. In other words, find the derivative of an implicit function. So let's go ahead and give you guys some steps. The first thing you're going to want to do is you're going to differentiate both sides of the equation with respect to x. So what that means is we're going to put a d over dx, with some brackets around the equation, just like that. That's what I mean. And you're going to go ahead and do what we've just been talking about all along. The next thing you're going to do is you're going to pull all the terms with y prime on one side, and then you're going to factor out the y prime. Now, this step is only necessary it's only needed if we have more than one y prime. Okay, so sometimes you have two y primes, sometimes you have only one. So for example, on this, let me back up on this problem here, like for instance, right here, we had two y primes, right? One there and one there. But on this one, we only had one. So you'll only need to do steps 2 and 3 if you have more than one y prime. Okay. Step 4 is to solve for y prime. Get the y prime by itself. Okay. So that's our goal, and that's the steps we're going to go through to find y prime. All right. So let's go ahead and do some. Okay. So let's start off with number 1. Oops. I went too far there. 5x squared minus 5y cubed equals 2. All right, so step 1, brackets, derivative, like so. Now we're going to go ahead and take the derivative of each piece. So what's the derivative of 5x squared? Since x is the input variable, or the value I'm doing respect to, and these match, just do a derivative like normal. So the derivative of 5x squared would be 10x. Next. Since these match, or sorry, they don't match, x and y, but y is a function of x, we're going to do the derivative like normal, but we're going to put a y prime next to it. And then finally, we're going to take the derivative of 2, which is 0, just a constant. So that's step 1. Now, steps 2 and 3 are only necessary if you have more than one y prime. But as you guys can see, I only have one y prime there, so it's not necessary to do that. So at this point, what I'm going to do is I'm going to get the y prime by itself. So the first thing I'm going to do is I'm going to add this whole expression here to the other side. And now I want to get y prime by itself, so I'm going to divide everything by 15y squared. And there's the derivative. Of course, if you can, you should probably reduce it. So 10 over 5 can be simplified to 2/5. And there's our final answer. Okay, so that's a pretty simple example. It's one of the easier ones. So let's go ahead and see if we can find you guys one that's equally easy to try out really quick before we move on to a new topic here. So why don't you guys try this one really quick and pause the video. When you're done, come back and check your answer. All right, so there's our answer to that problem. Took the derivative, got the y by itself, y prime I should say, and then I simplified it. All right. Let's go back to the last problem then, or the last page I should say, and let's go ahead and try another one then. So number 2. Now the rest of these are just kind of examples to kind of show you some other situations. Let me skip, I think I'm going to skip number 3 really quick, and instead I'm going to make up a different one. So let's say that I have the following here. Let's say I have 4x squared plus 5y squared minus, what would be a cool one to do? Let's go ahead and say tangent y equals 8. Let's say that. All right. So step 1, brackets, derivative. Here we go. They match, so it's a normal derivative. They don't match, but y is a function of x, so normal derivative with a y prime. And the letters match, so normal derivative, but with a y prime. And then finally, that's a constant, so it's 0. Okay, now in this case, notice that I do have more than one y prime there. So in that case, the directions that we are going to do steps 2 and 3. Steps 2 and 3 say make sure that the y primes are all on one side of the equation. So the easiest way to get all the y primes on one side is to move everything else away from them. So I'm going to move this 8x out of the way because it doesn't have a y prime. I'm going to put it on the other side. That way my 10y y prime and my y prime secant squared y will be on the same side that's opposite from the side of the negative 8. Okay. Now in this case, we have 2 y primes, right? So step 1 is to make sure all the y primes are on one side and everything else that doesn't have a y prime is on the other. Now the next thing you're going to do is you're going to factor out the y prime. Just pull it out like this. Divide it out. By factoring it out, it's no longer in 2 separate places. Now it's only in 1. So it's much easier to get the y prime by itself. All we have to do now is divide both sides by the 10y minus secant squared y. So those cancel. And over here now we have this. And there's my answer. So y prime is equal to, let me erase all this stuff so it's not in my way. I don't know if it'll let me erase it, but there you go. Y prime is equal to negative 8x over 10y minus secant squared y. Now, here's something that's a little weird. On a multiple choice test, you may not see this answer, but you may see this another answer that's a lot like it. Okay, you may see this instead. The reason why you can possibly get two different answers is because it depends on what you do to get the y primes by itself. Like up here on this step, I chose to move the 8x to the other side. But if somebody had chosen instead to leave the 8x there and move both of the y primes to the other side, they would have gotten this other answer instead. They're both correct. Okay, it doesn't matter. But how will you know you're looking at the right one? Well, the only difference between these two problems is that everything's got an opposite sign. So we have a negative 8x versus a positive 8x. A negative secant squared y, a positive secant squared y, a positive 10, and a negative 10. And even though all of them have opposite signs, why is that okay? Because if the top of the fraction and the bottom of the fraction have opposite signs, they cancel each other out anyway. So they're really the same expression, just written in different ways. So I want to make a note of that. Answer can be written in two ways. That's important for your multiple choice part of your exam because you may do it one way, but the answer that they offer may be the other one that's on there. Okay? So just change the signs of everything. So let's review this one again. Why did I give you this example? This example was given to you because we had two y's. And since we had two y's, we ended up with two y primes. And when you have two y primes, you have to do two extra steps. You have to get the y primes on one side and anything without a y prime on the other. Then you have to factor out the y prime and divide what's left. Okay, so that one is a little bit more involved. So let's go ahead and have you guys try one. I don't know if I have one of these on your slide. Let me see. I do not. So what I'm going to do is I'm going to give you guys one here. Let's try this. Go ahead and find the derivative of that function with respect to x. And when you unpause the video, you will see the solution. Okay, so step 1, find your derivative. That's what you should have gotten for your derivative. Step 2, move the y primes all on one side and anything without a y prime on the other. Step 3, factor out the y prime. Now, you could have also taken out a y and a 3. But because both of these can be divided by a 3 and a y also, but we don't do that. Just take out the y prime, okay? So factor out the y prime, and then the last step is to divide this big old chunk to the other side, and you end up with our answer. Now don't forget, your answer can look like this instead, depending on how you got the y prime by itself. All right, so that's that. Let's move on to some other types of examples here. Now, at this point, you guys, I've shown you a lot. The only other one that I would say is different is this one. So I would say go ahead and watch me do at least this one. I'm going to continue doing a few more. You do not have to watch anymore, but I'd say at least watch me do number 9 because that one is a little bit different. It's a little bit special. And practice that one. After that, I'm going to keep doing some, but you're welcome if you feel like you got it to stop watching and go do your homework, okay? So let's go ahead and do number 9. After that, you guys can stop watching if you feel confident. Okay, so here we go. What makes this one special is this expression right here. Why is that special? Because it's a product rule, okay? So let's start easy. The derivative of that is going to be 5. The derivative of that's going to be 0, so if you don't mind, I'm not even going to write it. There's no point. But now let's do the derivative of this. Now, we have a product going on here. I've got 5x being multiplied by y. That's my a, that's my b. So it's going to be a times b plus a times b. One of them's a prime here. The opposite one's a prime here. So A prime is 5. B is y. A is 5x. B prime, the derivative of y is 1, but since it's a derivative of y with respect to x, and it is a function of x, so 1y prime. Okay? So there's that. So let's simplify that a little bit. 5y plus 5xy prime equals 5. A lot of 5s there. That's interesting. Okay, so we want to get the y prime by itself. I think the easiest way to do that is to subtract the 5y on both sides. So now I've got 5x y prime is equal to 5 minus 5y. And then next what I would do to get the y prime by itself is I would divide both sides by 5x. And we have this. Now, here's another little interesting situation about this one. Sometimes you can reduce. So for instance, but it has to work for all three of them, all the terms. So here's a term, and here's a term. We could divide something out of all three of those. And what is it? It's 5, right? So it would be 1 minus y over 1. And so that can be your answer right there. Or you can just say 1 minus y. That would be fine as well. Okay? So let you guys try one of those. Why don't you guys try to do number 10. Pause the video. And when you're done, I'll have the solution for you. Okay, so here's our final answers here. Take the derivative. I rewrote it just a little bit more simple. But as you guys can see over here, here is the product rule for this expression. Then I got the y prime on the left side. I subtracted this 3x squared y to the other side. And I got negative 3x squared y prime equals this here. And then after that, I divided both sides by the negative 3x squared, and I got my answer. Don't forget, when you have a fraction, you can change the signs of all the terms. That is also another way of writing the answer. So now at this point, guys, I'm going to continue doing examples and giving people a chance to practice. This one's going to show a chain rule. This one's going to show derivatives with exponential functions. This one's going to have a chain rule with trig. So really, it's just more practice. There's not more to implicit differentiation than that. But just kind of putting all the rules together. So if you guys want to kind of see a variety of questions at this point, I would encourage you to keep watching. But if you feel like, I remember the rules, I'm good, I'm going to move on, that's fine as well. Let's go ahead, and I'm going to keep going. You're welcome to kill the video here and go do your homework if you like. But if you want to see more, I'm going to keep going. Here we go. So let's do this one really quick here. We have 4x squared is equal to y cubed plus 1 squared. So we're going to put that whole thing in brackets, and we're going to put a derivative symbol here. So the derivative of that's going to be 8x. This one is a chain rule. So the inside function is this, y cubed plus 1. The outside function is a square. So we're going to put the 2 in the front. And keep the inside the same. Times the derivative of the inside, which is 3y squared. And since we're finding the derivative of a y expression with respect to x, and y is a function of x, we need to put a y prime there as well. Okay? So if I were to simplify this a little bit, well, actually, before I simplify, what we can do is take all of this stuff and divide it out to the other side. And there's our answer. But they would probably simplify it a little bit by like putting these two things together. They might even go the extra step and distribute this in, although I doubt it, honestly. But I do see that they would probably reduce the 6 and the 8. So there's a few different ways that this answer can be written. I would say this is one way to write the answer. Or they might have it distributed inwards. So it could also look like this. Either one of those are good. I don't think on this one they would have the opposite sign thing happen. I mean, you could. It's just that since there was only, the y was already on one side, there's really no need to move things around like that. So it probably would just stay as is. But there's that one. So that's a chain rule. If you want to try a chain rule problem, here's one. You could pause the video and I'll have the answer up for you. Okay, so there's the solution there. Let's go ahead and take a look at another type of example. Let's do a trig one. This one probably won't be too mind-blowing. We've already done a trig one earlier today, but what the heck, we'll keep throwing some examples up just so you guys can get lots of practice. Questions like this are actually pretty important on the FRQ section of your AP exam. They have a whole section devoted to questions like this. So, all right, so let's do this one. Derivative of that would be 15x squared. Derivative of that is 0, so I'm not even going to write it. Cosecant. The derivative of cosecant is negative cosecant cotangent. And it's 3y squared is my input, times the derivative of the inside, which is 6y squared. And since we're finding the derivative of an expression with y with respect to x, and y is a function of x, we're going to put a y prime there. Okay? So now, I ran out of space, so these are supposed to be up here next to the rest of it, but I didn't want to write on top of the black stuff. So. Now what I want to do is I want to get this y prime by itself. So I'm going to divide everything on this side to the other side. So that's going to look like this. And the 6y squared, I think I'm going to put that in the front with the negative like that. And then we can probably reduce this 6 and the 15 there by 3, right? So 3 goes into 15 5 times, and 3 goes into 6 twice. There you go. I would say that's probably a good enough answer. They might put the negative on the top, because it doesn't matter which side you put that on. But anyway, you don't have to move the negative. All right, so if you wanted to try one of those, I don't know. I think I'll skip it. I mean, you can do it if you want to, but it's almost identical to the problem. So if you want to try it, you can. But I'm going to go ahead and move on to something different. Let me do number 7. So I'm going to do number 7, which is an LN, and then I'm going to let you guys do number 8, which is an E. They're kind of similar, but they're also a little bit different, so we'll see how you guys do. So like I said, we're just kind of giving you guys some exposure to various problems. So here we go. Ln of 3y squared is equal to 2x cubed plus 3. And we want to find the derivative of this thing with respect to x. So I'm going to start on this end. That's 0, so it just goes away. This one's going to be 6x squared. This one. All right, so we learned how to do derivatives of logs last lesson. So the way the derivative of logs work is we're going to do a chain rule. We do the derivative of the outside, which is ln, so that would be 1 over the inside, times the derivative of the inside, which would be 6y, times y prime. Next, if we simplify that a little bit, I end up with 6y, y prime over 3y squared. Just multiply the 6y, y prime to the top. We can keep simplifying here too. The y here will cancel out one of the y's on the bottom. The 3 will go into the 6 twice, so now I have this. And remember, my goal here is to get the y prime by itself. So how do we get the y prime by itself? Well, the first thing I do is I get rid of the y on the bottom. You do that by multiplying by y. Because if you do that, they cancel, right? But whatever you do to one side, you do the other. So now I've got 2y prime equals 6x squared y. Now what do we do to get y prime by itself? We would divide, right? So if I divide both sides by 2, 2 goes into 6 3 times, and so your final answer here would be 3x squared y. All right. So last one we'll let you guys mess around with here today is number 8. So I want you guys to try it on your own. Pause the video, go as far as you can with it, and when you unpause the video, you'll see the solution. Okay, so what we have here as the final answer is a circled one. So if you take the derivative of e to the 3y cubed power, the derivative of any e is always going to be exactly the same as the original, but then when you do the derivative of the exponent, or the inside function itself, this is a chain rule. So the derivative of 3y cubed is going to be 9y squared, and since we're finding the derivative of a y with respect to x, we're going to put a y prime there. Derivative of 3x is 3, and derivative of 5 is 0, so we don't bother putting it. Divide both sides by the 9y squared and the e to the 3y cubed to get the y prime by itself. And we get this. Then we can reduce the 3 with the 9, and we have our final answer. Okay? So that's it. Lots of practice there. Hope that's helpful to you guys, and we will see you guys next week.